Next we have is the real numbers. So we start with the definition of rational numbers. So the set of rational numbers, it is denoted by Q, and it is defined as it has elements of the form A by B, or you can write, if you don't want to write it like this, you can write it is consisting of all the elements X such that X is of the form A by B, where the denominator B is not equal to 0. A and B, they are the integers, and HCF of A and B, that is equal to 1. Why this last condition is over there? Because we know that we don't want the elements to be repeated in the sets. Repeated in the set means we are talking about the condition that if we have the elements 2 by 2, 3 by 3, 4 by 4, we don't want all these elements to be included in the set. So all these elements, these are equivalent to 1. So only 1 will be written over there. So this is the correction of, this is how the set of rational numbers is defined, and it is important to note that this set, it is represented with Q. Now if we talk about the properties of these numbers, then the first property we have is that rational numbers are closed under addition, subtraction, multiplication and division. And division is except for 0. Except for 0 means we are talking about that A and B, they are divided, then this B should not be equal to 0 whenever we are talking about the division. Then A by B, that also, if A and B, they are the rational numbers, then the answer we will have over here, that is also a rational number. Next is solving the equations. So when we were talking about the integers, we have seen that if we have the equation of the form 2x is equal to 1, this implies as x is equal to 1 by 2, and this does not belong to the set of integers. But when we are talking about the equations of the form ax is equal to b, and we are considering the rational numbers, then we can solve these kind of equations. And what is the limitation for the rational numbers? That if we have the equation of the form x square minus 2 is equal to 0, then the solution we will have, that will be plus minus square root 2. When we have x square minus 2 is 0, we will get x square is equal to minus x square is equal to 2. So x is equal to plus minus square root 2, and these numbers, these are not the rational numbers. So rational numbers are not sufficient to solve these kind of equations. Next we have is the representation of rational numbers on the number line. So this is the number line shown over here, and we are talking about the rational numbers. This is the neutral number 0. We are showing the natural numbers 1, 2, 3 and continue like this. We will have minus 1, minus 2, minus 3, these are the integers. Then between 0 and 1 we will have the rational number 1 by 2, between 1 and 2 we will have 3 by 2. So all the rational numbers, they can be represented on the number line. Suppose I am talking about the number 3 by 2. So how we are going to represent it? We can write 3 by 2 is equal to 1 plus 1 by 2. 1 plus 1 by 2. So how we are going to represent it? We are drawing the line over here. This is the point 0. This is 1. This is 2. 1 is already there. It means we are saying 1 plus 1 by 2. 1 is already there. After that we require it is 1 by 2. We want to divide this portion in 2 parts. We will draw a line over here. I am talking about this distance. This is 1 unit distance. This is half unit distance. This distance is 1 unit distance. So this point we are having, this is basically 1 plus 1 by 2, that is equal to 3 by 2. This is how we can represent the rational numbers on the number line. Next we have is the decimal representations of the rational number. So if any rational number is given to us, number of the form p by q, it is rational, we know. So if we are dividing p with q, if we are dividing p by q, or we are writing the number of the form a by b, I am not considering p and q, it will create the confusion. I am talking about the number a by b. Definition we have, b is not equal to 0. We are dividing a by b, you know there will be a quotient and there will be some remainder whenever we have a number of this form. This is the case. Then we have two cases. When we were talking about the Euclid's division lemma, we were saying that this q should be an integer. Now in place of integer, we are talking about the case when this q is a rational number. Then we have two cases for this r. Either this r will be equal to 0 or this r is never 0. R will be 0 means, suppose I am talking about the case 1 by 4. When I will divide this, I will get it is 0, 2, 8, 2, 0, then 5, 2, 0, remainder is 0. So we are saying, what kind of decimal representation is this? This is terminal or terminating decimal representation. That is, the remainder becomes 0 after a finite number of steps. So this kind of representation, it is called the terminating decimal representation. And another representation for the rational numbers, it is the non-terminating and repeating representation. So first of all, we will look what is non-terminating over here. What non-terminating means over here. So if we are talking about 1 by 3, we are dividing 1 by 3, we are talking about this value. Then what will happen over here? We will put decimal over here, we will get 0. It is 3 3s are 9. We will get again 1. We will get 0. 3 3s are 9. We will get again 1. And this process will continue like this. And the remainder, it never becomes equal to 0. So if we look at the quotient over here, the quotient we have, it is non-terminating. But it is important to note over here that whenever we are talking about the rational numbers, this quotient will be non-terminating in this, when it is non-terminating, whenever it is non-terminating. First case we have seen, either the quotient we will obtain, that is terminating. Second case we are talking about, when it is non-terminating, then it will be repeat. If it is non-terminating, then it will be repeating. So what we obtain over here is that the rational numbers that we have, either they have the terminating decimal representation, or if it is non-terminating, then it is the repeating. Now let us consider another case. We are talking about the number 0.25. We are talking about the number 0.252525 and so on. We can write this in the form 0.25 bar. Bar represents that this 25, this block 25, it is repeating again and again. Now consider another case. If I am talking about 0.01 001 0001 0001 00001 and so on. What is happening over here? That there is no fixed block that is repeating. Over here, this 01 is there, then 0001 is there, then 00001 is there, then there is no repeated block over here. So we are saying these kind of decimals we are talking about, these are non-terminating. These are not terminating. This will continue like this, and they are non-repeating. Neither they terminate nor they repeat. These kind of decimal numbers we are talking about, or these kind of values we are saying, these are called the irrational numbers. These kind of numbers, these kind of decimal numbers which are non-terminating and non-repeating, these are called the irrational numbers. So if we talk about the geometric representation, we try to answer first of all these two questions, then we will move towards more numbers, more irrational numbers. This says, can we represent the diagonal of a unit square on the circumference of a circumference of a unit diameter circle on the number line? So in the first part, we are saying, can we represent the diagonal of a unit square? We are talking about a unit square. Suppose we are saying unit square means a square is there. The sides of this square, they are 1. Now what is the length of the diagonal of this square? We will use the Pythagoras theorem. This is 1, this is 1, so this value it is square root 2. We want to represent this length, this number square root 2 on the number line. So what we can do? We are saying we will plot the line over here. This is the point 0 we have. This is the point 1 we have. These are the 2 points that we have. Now from this point 1, we have this 1 over here. We draw a unit square like this. We draw a unit square. The length we have, this is 1, this is 1, this is 1, this is 1. If I draw the diagonal over here, this length we are saying this is square root 2. Now I will keep the tip of the compass at this point, the pencil at this point, and I will draw an arc like this. So this length, it is square root 2. When you will draw the arc like this, we are saying that this length we have, it is square root 2. So it is important to note over here that if we have to plot square root 2 on the number line, we cannot use the decimal representation of square root 2, because it will not give us the exact point, because we don't have the exact value in decimals for this point square root 2. So in place of using the decimal representation, we use this kind of geometric idea to plot this point square root 2 on the number line. So this thing represents that we can represent the irrational numbers on the number line. Now the second part of this, it was the circumference of a unit diameter circle. We have to plot this. A circle of whose diameter is 1 unit, it is given to us, and we want to plot that on the number line. So let us see that how we can plot that point. So suppose we are saying we have a circle whose diameter is 1 unit. So what is the circumference of this circle? The circumference C that we have, it is 2 pi r or pi d. So that will come out to be pi units. It means we want to plot the point pi on the number line. So what we have done? This is the point 0 that we have. We have drawn a circle over here. The diameter of this circle, it is 1 unit. The diameter of this circle, it is 1 unit. Now we cut this circle at this point. At this point we cut this circle and we start opening this circle like this, and we start opening this circle like this. When you will open this circle like in this way, you cut this point, you open this circle in this way, the end point this end point, it will reach when we are opening it. It has reached over here, then it has reached over there. We open it like this. We open it like this. We open it like this. It will reach somewhere over here. So what is this length? Wherever this is the one end point of this circle, when we open this will become a straight line. This is one end point, this is the another end point. This point where the another end is lying, the length of this line, that will be equal to pi units. So this is basically representing the point pi on the, this is how we can represent the point pi on the number line. So these were some geometric ideas that how we can represent these points, square root 2 or pi on the number line using these geometric ideas. Next we have listed some well-known irrational numbers. When we are talking about square root 2, it is 1.414213. You should remember these values, that what is the value of square root 2 when we are talking in decimals. It is 1.414213 and so on. So it is basically the length of the diagonal of a unit scale. We are talking about square root 3. Square root 3, where it appears? We are saying it appears in equilateral triangle geometry, and we are talking about the equilateral triangle. We have use of this. So many times we use square root 3. It has other uses also, but at this place, when we are talking about the area of the equilateral triangle, or we are calculating the formulas related to triangle, square root 3 is used over there. So when we are talking about this value square root 3, the value we have, approximate value we have, it is 1.732050 and so on. So at least up to 2-3 decimal places, you should remember these values. Square root 2 is 1.414, square root 3 is 1.732. We are talking about square root 5. This is related to the golden ratio. Golden ratio is also a number. So we are saying square root 5, it is 2.236067 and so on. This value is also irrational. Similarly, we have listed some other number. This is the number E we have. You should remember the value of E. It is 2.718281. At least up to 3 decimal places you should remember this value. It will be used at several places because it is the base for the natural logarithm that we are going to use in our calculations. Then we have the number pi. It is 3.141592. This is used when we are talking about the circle, area of the circle, circumference of the circle. Pi is generally used over there. This is the number 5 we are talking about. Its value is 1 plus square root 5 by 2. It is 1.618033. And this golden ratio, you can try to find several examples related to golden ratio. This is an interesting number that is used in art, that is used in nature. It is all about symmetry. So you can just search this number and you will find several examples related to it. And if we represent these numbers on the number line, we are saying this is the point 0 we have 1, then root 2 somewhere over here, then we have 5, this is 2, E, 3, pi, and similarly these are the negative of these numbers. So these are certain irrational numbers. That is, these are the numbers that have decimal representation that is neither terminating nor repeating. Next we talk about the number pi. So whenever we are talking about this number pi, it is important to note over here that pi is an irrational number. We use several values of pi. Sometimes we write, this is the symbol pi we are using. This is an irrational number. The number is this. 22 by 7, 3.14, they are not pi. Those are the approximate values of pi. When we are talking about the number 4, you write 4. When we are saying the number pi, pi is this number. This is the representation of pi. There are several representations. We are talking about the approximate value of pi. It is this. Now we approximate this with various different values. Suppose I am talking about 22 by 7. When I am saying 22 by 7, clearly this is of the form P by Q, where Q is not equal to 0 or A by B it is, B is not equal to 0. So this number 22 by 7 is a rational number, and it is used as an approximation to pi. And when we calculate the value of 22 by 7, the value we obtain it is 3.14287. If we compare it with the value of pi, you will see this is 314. 314. The rest of the digits, they do not match with the value of pi. So we are saying that whenever we are using pi as 22 by 7, the approximate value it matches up to 2 decimal places. If we are using the value of pi as 355 upon 113, the value of this is given over here. This is a rational number. The representation is terminating. The representation of this number, it is a terminating decimal written over here. Now we are saying, look at this value. It is 141, 141, 59, 592. Then it is 9 over here, and it is 6 over here. So we are saying this value it matches with the value of pi. The decimal representation of this number 355 by 113, it matches with the exact value of pi up to 6 decimal places. Likewise, we have several values over here. If we are talking about this value, if you calculate this value, you will obtain, this is the decimal representation, it will match with the value of pi up to 15 decimal places. So these are all rational approximations of pi, but pi itself is an irrational number, that is non-terminating and non-repeating decimal number. But these values, when we are using, generally we use the value 22 by 7, or we can use the value 3.141 or 3.14. So depending upon the situation, you can calculate or you can use an approximate value of pi. But these are just the rational approximations of pi. These are not the values of pi. The pi itself, it is a number written in this form, and its decimal representation, it is an infinite decimal representation, that is non-terminating and non-repeating. Now another interesting thing to note about pi, it is the Feynman point. Now suppose we start writing the value of pi. If we start writing the value of pi, is an interesting pattern is seen. We are saying at 762nd decimal place, this 9 is repeated 6 times. When we are calculating the value of 3.141 so on, we calculate it like this. We are talking about the 762nd place. The points we have, it is 9999999. The next digit is not 9. Over here, it seems like that the 9 has started repeating, but it is not the case. Even though the 9 appears 6 times together, after this the next digit will be different. Now why this is interesting, or I have noted over here, this is called Feynman point, because this is called Feynman point, named after the physicist Richard Feynman, and he joked about it while he says that if someone memorizes the value of pi up to 762nd place, he can say, after this he can say 9999999 and so on, which implies that pi is rational, but it is not. So this is an interesting pattern in the value of pi, that this 9 is repeated 6 times at 762nd place, but still pi has non-terminating and non-repeating decimal representation. Next is the definition of the real numbers. So till now we have seen natural numbers, then we have whole numbers, then we have integers, then we have rational numbers. After rational numbers we have seen the set of irrational numbers, rational numbers, and we have seen the set of irrational numbers. So all these numbers, either they are rational or they are irrational, they are called the real numbers. And it is interesting to note over here that we cannot describe the real numbers in the roster form, because these real numbers, they do not follow any particular pattern. If suppose I am talking about the number 1, there is no next number. If suppose I want to write the real numbers in the roster form, I have written 1. What will be the next number? It is not that easy. So what will happen over there? Suppose I am saying 0, so on up to 1, so on up to 2, so on up to -1, so on up to -2, and so on. But there is no not this kind of representation. It is not much interesting to write the things in this way. So in place of writing this, we are just saying this thing that it is not easy to describe, or it is not possible to describe all the real numbers, because they do not follow a particular pattern in which we can write these numbers, or we can say that we generally write the set of real numbers in the set builder form. So this is the definition of real numbers. Again, if we list the properties over here, we are talking about the closure property. So the real numbers, they are closed under addition, subtraction, multiplication, and division, except for the number division, except for the number 0. So we are saying if we add, subtract, or multiply two real numbers, the answer is a real number. If we divide two real numbers, a divided by b, b should not be equal to 0. The answer that we will have, that will be a real number. The answer we obtain, that will be a real number. And the real numbers, they are able to solve the equations of the form x raised to the power n is equal to a for all a greater than equal to 0, and for all n belonging to the set of natural numbers. Why we are saying this kind of situation? Because when we are talking about rational numbers, we are saying we cannot solve the equations of the form x square minus 2 is equal to 0. So this is basically x square is equal to 2. We will obtain x is equal to plus minus square root of 2. But when we are talking about the real numbers, we can solve these kind of equations also, because the answer in this case, we are saying it is a real number. It is an irrational number, and all rational and irrational number, they are together called the real number. So we are saying that we are able to solve these kind of equations with the real numbers. Now consider this equation again. When we are talking about the equation x raised to the power n is equal to a, we are talking about this condition over here, that a should be greater than equal to 0. Now suppose I am talking about the equation x square plus 1 is equal to 0. When I am writing x square is equal to minus 1, is there any real number whose square is minus 1? Answer we have, it is there is no real number for which x square is equal to minus 1. So to solve these kind of equations, what we are going to do, let us look at the representation of the real numbers. I am saying this is the number 0 we have, this is the number 1, 2, minus 1, minus 2. All rational and irrational, they are included over here. So this line, we are saying this is the real line. We are saying any point on this line, that is a real number. This line is completely covered. Now we want to solve this equation x square plus 1 is equal to 0. There is no place on this line where we can solve this equation. So what we are going to do, we are going to add another dimension to it. We will add another dimension to it. We'll now, to solve these kind of equation x square plus 1 is equal to 0, we will consider the plane. I'm not going into the detail of this right now. This thing we will study when we will talk about the complex numbers. So we leave it at this place, that the real line up to this equation x raised to the power n is equal to a is greater than equal to 0, and n belongs to n, we are saying. All the solutions lie on the real line. When we are moving towards the equation x square plus 1 is equal to 0, we are talking about a is negative. There is no place for the solution on this line. We will move towards the plane that will be called the complex plane, that we will study when we will talk about the complex numbers. So this was all about the real numbers that you should know right now. Things as we will move further, we will list more properties over there. Right now you should know up to this point. Next we have is certain linear inequalities. We are going to talk about linear inequalities in one variable. Very basic idea related to inequality. So we are saying if we have ax plus b is less than c, these are the inequalities, the forms we have. We are talking about equation 2x plus 3 is less than 7. So this is an inequality. Less than sign is there, this is not an equality. If equal to sign is there, we will say it is equality. Less than sign is there, it is inequality. Ax plus b is less than equal to c. Inequality. Why linear? Power of x, that is 1. Similarly, x plus b is greater than c, or x plus b is greater than equal to c. Where we are saying a, b, c, these are the real numbers. A is not equal to 0. The coefficient of x is not equal to 0. These are called the linear inequalities in x. Linear inequalities in x. One variable is there. Linear because power of x is 1. Inequality because this inequality symbol is over there. Next we have is the term replacement set, or the domain of the variable, and the solution set. So whenever we are talking about an inequality, suppose I am talking about the inequality x is less than 6. We are talking about certain values of x. The set where these values we are given set from where this x can take values. X can take values. That is called the domain of the variable, or the replacement set for x. And the possible values for this x, that is called the solution set. So let us consider the example over here. We are talking about x is less than 6. First case we are saying if the replacement set is set of natural numbers, we want x to be a natural number. The solution set will be, we are talking about x can be a natural number, and x is satisfying x is less than 6. It means we are talking about all the natural numbers less than 6. X is all the natural number less than 6. Natural number less than 6, they are 1, 2, 3, 4 and 5. These are the natural numbers less than 6. The replacement set is, or the domain of this x, it is n natural numbers. The solution set we have, it is 1, 2, 3, 4 and 5. We are talking about whole numbers. If the replacement set is whole number, we are saying find the solution set of x is less than 6. When the replacement set is whole number, we want all the whole numbers which satisfy x is less than 6. Whole number which satisfy this condition, they are 0, 1, 2, 3, 4 and 5. These are the whole numbers which satisfy this condition. If the replacement set is integers, we want all integers which satisfy x is less than 6. The domain of this x now, it is integer. The answer we will have, it is so on up to -3, -2, -1, 0, 1, 2, 3, 4 and 5. This is the answer in this case. When we are saying replacement set is integer, these are the integers which satisfy this equation. So these are the two terms we have. One is the replacement set or domain. These two terms, they can be used in any term you can use. Either you can say replacement set or you can say domain of the variable. The next term we have it is the solution set. Next we have listed certain rules related to inequalities, that whenever we are solving the linear equalities you can use these equations. These rules you already know, you have studied in your previous classes. This is just a review. We are saying adding the same number or expression to each side of an inequality does not change the inequality. If I am talking about x minus 4 is less than 3, the rule says adding the same number or expression to each side of the inequality doesn't change the inequality. If suppose I add 4 on the both sides, this inequality will not change. The answer I will obtain it is x is less than 7. This is our first rule. Second rule is subtracting the same number or expression from the each side of an inequality does not change the inequality. If we are talking about x plus 5 is less than say 7, I am subtracting 5 from both sides of this inequality. We are saying the inequality will not change. I am getting x is less than 2. So when we are adding or subtracting same term on both sides of this inequality, it will not change the inequality. Next is multiplying or dividing each side of the inequality by the same positive number. This term positive is very important over here. I'm talking about x by 2 is less than 5. I multiply both sides of this inequality with 2. X by 2 into 2, 5 into 2. Clearly this number 2 is a positive number. Inequality will not change. Inequality will remain same. We will get x is less than 10. We will obtain x is less than 10. Now come to the case, what if this number is negative? The number we are multiplying or dividing both sides, if it is negative, what will happen? We will say if we multiply or divide a number that is negative number on both sides of the inequality, it will reverse the sign of inequality. Minus 3x is less than 9. I am dividing both sides of the inequality with minus 3. This is a negative number. What we will do? This is less than sign over here. This will change the sign of inequality and it will become greater. I am again repeating. If the number we are multiplying or dividing on both sides of the inequality is negative, when we were talking about addition and subtraction, we were not talking about number is positive, negative, whatever the number is, there is no change in inequality sign. When we are multiplying the number or dividing a number and the number is negative, it will change the sign of this inequality. This minus 3 gets cancelled. You will get x is greater than minus 3. So this is very important to note over here. Always keep in mind that whenever we are multiplying with a negative number or we are dividing a negative number, we have to reverse the sign of the inequality. Next we have is transposition. So using rule 1 and rule 2, we can drop any term from one side of the equation and putting it on the other side with the opposite sign. X plus 4 is greater than equal to 10. We are talking about two cases. One thing we can do is x plus 4 minus 4 is greater than equal to 10 minus 4. We are writing x is greater than equal to 6. What transposition says, in place of doing this, we can just shift this term on this side. we are just writing x is greater than equal to 10 minus 4. Whenever you are shifting this term on this side, this sign gets, if it is negative sign, it will become positive. If it is positive, it will get negative. We are saying that we have to use the opposite sign. So answer, x is greater than equal to 6. These are very basic calculations that you have studied in your previous class. So I am just trying to make you recall these ideas. Next is transitivity in the inequalities. So transitivity means we are saying if A is greater than B and B is greater than C, then we will have A is greater than C. Just simple calculations are there. These will be used just in the simple calculation that if A is greater than B, B is greater than C, then A is greater than C. Next we have is adding or subtracting two inequalities. These inequalities, these are given to us. We are saying A1 is greater than B1, A2 is greater than B2. These two inequalities are given. We can add these inequalities. What we will obtain, we will get A1 plus A2 is greater than B1 plus B2. We are talking about A1 plus A2 is greater than B1 plus B2. It is very important to note both these signs, they are same. We are not doing this thing A1 is greater than B1, A2 is less than B2. What you will do? A1 plus A2, B1 plus B2. What sign you will use over here? So this kind of idea we are not going to use. We are saying if A1 is greater than B1, A2 is greater than B2, then A1 plus A2 is greater than B1 plus B2. Similarly, for the n terms we can use, this is for the addition. Similarly, we can use for the multiplication, that the two inequalities they are given to us. We are saying A1 is greater than, we are saying A1 is greater than B1, A2 is greater than B2. We can multiply these terms, we will obtain A1 into A2 is greater than B1 into B2. What we mean to say is 4 is greater than 2, 6 is greater than 3. You can add this, you will get 10 is greater than 5. You can multiply this, you will get it is 24 is greater than 6. So these are just the basic results that you can use whenever you are talking about these calculations. So next we have listed certain problems that you can try at your own. So these are the questions that we have. Based upon this,